something like architecture of a very long instruction word computing, right? On the right hand side you can see there are 4 variations, how many inputs are coming and how many data are coming, right? So based on that we can have SIST, it is the minimum one. There is one instruction from the instruction pool, there is one data from the data pool, and these two are given to a processing unit. PU stands for processing unit. So one data, one instruction. On the right hand side you can see MISD. So I'll be getting multiple instructions. So instruction panel pool, I am getting 2 instructions are coming out and 2 processing units are there, but single data, right? So in that case the same data is supplied to the first unit as well as second unit. I think from the diagram you can easily view that. Then the third diagram on the bottom side you can see SIMD. So there is a single instruction which is taken away from this instruction pool, but it is processing with multiple data. So 4 data are coming from this data pool, right? And the fourth case is MIMD, which stands for multiple instruction and multiple data. So here actually what happens, my data pool consisting of 4 data and will be giving 8 such data outputs, right? And from the instruction panel I will be taking 8 outputs, right? So 8 processing units will be processing different inputs from the instruction and the data, right? So these are all the architectures of VLIW and the SIMD to MIMD case. And what are the fundamental issues in the hardware software co-design? Here the control architecture implements the finite state machine, right? I think finite state machine you should have studied your digital system design or something like that, some paper. And this finite state machine, it has a state register and the combinational logic circuits. And the state register holds the present state and the combinational circuits implement the logic for the next state. So at any point of time, the system will be one state, and based on the inputs or based on the state that is available, it will switch over to some other state. So there will be a state movement will be there, right? And the data path architecture is best suited. Already we discussed about the data path architecture. So the data path architecture is actually, we can say it's a collection of so many instructions, we can say, right, from the input to the output. How my data is flowing, right, from the input to output. Say for example, in a FIR filter you should be knowing there are 3 operations needs to be performed. The first one is actually the delay element, the second operation is in multiplier, the third operation is an accumulator. So the data is coming inside and that will be processed by these 3 units. Maybe it's a 1 tap filter to 8 tap filter, whatever it is. Suppose 8 tap means you will be having 8 delays, 8 multipliers and 8 accumulators, right? So in those cases the data is getting added and the final result will be giving. So this is the basic architecture of a data path architecture. It contains port that connects the data to multiple buses, right? So the data is taken from the buses, right? And most of the time the arithmetic units are connected in parallel, right? So that more simultaneously you can process more number of data. Fine. And this finite state multi-machine data path architecture combines the controller architecture with the data path architecture. So both the things are combined together. Already in the finite state machines you might have studied about 2 finite state machines. One is called Moore, the second one is called Mealy. In the case of Moore finite state machines, the output depends only on the state that is available, right, before transition. And in the case of Mealy state machine, the output depends on the input and the state. What is the input and what is the present state? Based on these 2 factors, the system will move to the next state. Alright, so it implements a controller with the data path. The controller generates the control input, whereas the data path processes the data, right? The data path contains 2 types of IOs, out of which one acts as a control port. Normally we call it as control bus, data bus and all those things, right? So in a similar way there will be a control port will be available. And the second one is the IO port interface, where my data will be flowing from different parts of my embedded system. And normally the data path is implemented in a chip and IO pins of the chip act as a port to read the data or output the data. Fine. The complex instruction set computing, already we have discussed this, so it does not again repeat the same thing. One example they have given for the CISC processor, which is actually 8051, right? When the instruction is complex, what happens? The number of instructions will be reduced because each and every instruction will be doing multiple functions, right? Say for example, if you write MAC, right, it's a multiplier accumulator unit. So first it will multiply two data, then it will accumulate the next data, then that will be giving the results. So instead of writing a multiplication followed by an accumulation followed by giving the result, you can just use a single instruction, something like MAC, so that all the three operations will be performed. So this is actually the case of a CISC processor, right? A complex instruction set computing processor. Fine. So reduced instruction set, again the number of instructions will be reduced, right? So it requires the execution of multiple RISC instructions to perform a complex operation. The data path of the RISC architecture contains a large register, right, file for storing the operation, operands and output. RISC instruction set is designed to operate in registers and it supports extensive pipelining, right? And VLIW already we discussed. There will be multiple functional units, something like there will be so many ALUs will be there, multipliers will be there. And the VLIW instruction packages one standard instruction per functional unit, right? So we are going to take one sample instruction from each and every unit. And the parallel processing is possible. The parallel processor architecture implements multiple concurrent processing elements, and each processing element may be associated with a data path containing register and local memory, right? I think these things are there. And a single instruction, multiple data, multiple instruction, multiple data, already we have seen this. So these are all the different architectures there. And in MIMD architecture, the processing elements execute different instructions at a given point of time. The MIMD architecture forms the basis of multiprocessor systems because, say for example, in the previous example you might have seen there are 8 processing units are there. So it takes some 8 different data and 8 different instructions that gets executed. So it's used in the multiprocessor instruction set. The P is in a processing elements, right? In a microprocessor or a multiprocessor system communicates through a mechanism like shared memory, because whenever there are more number of processors working simultaneously, then the data sharing is actually very critical, right? So the same data should not be overwritten by some other microcontroller. So each and every microcontroller may be given a separate memory location where it can store its own data of processing, right? So that is actually the case. And the next thing is selecting a language, right? Once now actually we have selected what about the hardware, different architectures of hardware. We can see what are the possible hardwares. One is actually the CISC based hardware. Then we have seen data path hardware, then RISC based hardware, right? So we have seen different VLIW was there, SIMD, MIMD processors are there. So different architectures we have seen. Once the hardware is in, now we will get into the software. How I am going to select my software for my embedded system application. So there are plenty of software languages are available, of course you should be knowing. And a programming language captures the computational model, what type of computation need to be, data manipulation need to be performed. And a model can be captured using multiple program languages. So there are C, CPP, C#, Java, etc. there for this. Again, latest we can have the Python is also there, right, which is mostly used, right? Or there are some hardware implementations of software, something like Verilog or VHDL or System C, whatever it is. So these are all useful as implementing a hardware using a software, using a programmable hardware, right? So already I think you have studied about this VLSI design and Verilog already in your another paper. And in a similar way, we have to write a suitable software here in order to process all those data. Fine. On the other hand, a single language can be used for capturing a variety of models, right? And then CPP is actually a good candidate for capturing an object-oriented. Most probably, we can write the code in CPP in order to take the data, capturing the data, we can say. The only prerequisite is selecting a programming language is the language should capture the model easily. So whatever may be the model, the data should be easily taken from the model, right? If that is there, you can select or you can go for any type of language, right? Then now we have seen the hardware and software. Now the partitioning system requirements. So from an implementation perspective, it may be possible to implement the system requirements in either hardware or software. So it can be used either as a hardware implementation or a software implementation. So it's a tough decision to make it. But however, Various hardware software trade-offs are used for making a decision on transfer, on implementing which part of the hardware, which part of the software. In general, the hardware software partitioning.